In section 3.7, implicit differentiation, we're going to first learn about what an implicit equation is. Then we will go ahead and figure out how to take their derivatives. Now, we will see this again in application in 3.10 when we talk about related rates. The most common thing that we'll be taking the derivative with respect to is time, because everything changes with respect to time. But for now, let's consider the following equations. They're implicit equations, and we've actually worked with the one over here on the right before. X squared plus y squared minus 25 equals 0 is an equation for a circle, and we're more commonly used to working with the positive 25, and you can get that over there, and you can see we have a circle with a radius 5. In the middle right here, we have a parabola that is basically fallen over. How tragic. But you can see the idea of y equals x squared in this. If you were to solve this equation for y squared or x, you would have this y squared equals x, which is pretty close to what we've been working with. The square is just on the other variable. Then there's this guy over here on the left, x cubed plus y cubed minus sine x equals 0. Well, we'll find that we actually can't solve this for x or for y. In the cases over here, you can see, for example, the circle, you could solve it for y, and you could write it in terms of two functions. In the same way, you have plus or minus the square root of x when you solve this middle one for y. And the thing to note is these graphs as a whole do not represent functions. These equations do not represent functions. But, I mean, if you look at different pieces of them, each little piece of them could pass the vertical line test, but as a whole, they do not pass the vertical line test. Now, what makes them implicit? Well, let's think about something we've been working with already. So something like y equals x squared plus 1. This is an explicit relationship because you can go ahead and plug in some value for x. Let's say 1. And when you do, you're going to get some explicit value for y, in this case, 2. But let's consider the circle. If you were to plug in a value for x, let's say 1, well, let's see, that would be right here on the graph. You don't have a single y value, you have two y values, one up here and one down here. So the relationship is not explicit, but there still is one. And even over here on the graph on the left, that this x value has 3 y values associated with it. So each of these define an implicit relationship. And one way we could notate these equations is just kind of using this notation. When an equation f, capital F, of x, y equals 0 is difficult or impossible to put in the form of y equals f of x, we'll need to use a new technique to find the derivative. But again, this notation is just really saying, hey, we have an equation that we need to plug two things into. So let's go ahead and figure out how to take the derivative of an implicit equation. So let's look at that following parabola. We want to find dy dx if we're looking at the equation y squared equals x. And again, we're asked to find the derivative with respect to x. One way we can go about doing this is just taking the y squared equals x and solving this for y, because we're asked to take the derivative of y. So if we take the square root of both sides, we find that y is equal to plus or minus the square root of x. And, well, we have two equations here, so we could really say y1 is the positive part of the graph, and y2 is the negative square root of x, so the part that is in the fourth quadrant. Now, we could take the derivative of each of these. We can say, okay, the derivative of y1 with respect to x is just 1 over 2 square root of x. Again, we're just using the power rule, rewriting the square root function as x to the 1/2, gives us dy1 dx. And of course, when we take the derivative of y2 with respect to x, we get negative 1 over 2 square root of x. So again, we have y is equal to plus or minus the square root of x, but it would be really inconvenient to have to split this up every single time. And we'll even find that we can't even split it up to separate functions in a lot of cases. So let's go ahead and approach the same problem in a different way using what we learned about the chain rule. So this second, and I should say really usually necessary method, so I'm going to say usually, and we'll find that it's really easier than what we did last time. We just have to do it a few times to figure out what's going on. So what we're going to do is differentiate both sides of y squared equals x with respect to x, treating y as some differentiable function of x. And we saw in the last example, y was equal to plus or minus the square root of x, and it'll be the same scenario here because we're using the same equation. So how are we going to do it? Well, let's go ahead and see what we have written. We have given. We have y squared equals x. But instead of solving for y this time, I'm going to consider y as a function of x. So we have f of x squared, and that will be equal to x. And again, this is what we're used to. Y is equal to f of x. Now this is a composition on the left. So when I take the derivative, let's take the derivative of both sides now. When we take the derivative of the left-hand side, the outer function is the squaring function. So the 2 comes down, and then the inner function is left alone. And we're going to now need to multiply this by the derivative of the inner. And again, that's just f prime of x. Now, the right-hand side, the derivative of x with respect to x is just 1. Now, it may be a little confusing taking this f prime of x around, so what may be easier just to translate this back to the y. So that is to say, we have 2 times y prime equal to 1. So this is another way to notate it. And again, another way to even notate this is using the differential notation. That is to say, we have 2 times y times dy dx, and that's equal to 1. And again, we're going to need that bottom notation quite a bit when it comes to section 3.10 because we'll have to pay attention to what our variable is that we're respecting. But for really this lesson, I'm going to go ahead and use this middle one. So how do I find the derivative? Well, dy dx, or y prime, just solve for it. So what I have to go ahead and do to solve for it is just go ahead and divide both sides by 2y. So we find y prime is equal to 1 over 2 times y. And if you really look at this y is the same thing as mentioned above. So this is 1 over 2 square root of x, and of course the plus or minus could come out front, but what we have right here is maybe a cleaner notation because we're just saying, okay, we don't have an explicit relationship, so let's not worry about getting back to it. So we can just say that y prime is equal to 1 over 2y. So in this example, where we're asked to use implicit differentiation to find dy dx if we're given this equation. And again, this is one of those equations that we cannot easily solve for y, so we'll have to go ahead and use that method from the last slide. So let's go ahead and first just rewrite the problem. So we have 2x cubed minus 2y squared, 3y squared equals to 8y. And what we're going to do is we're going to differentiate both sides with respect to x. So I'm going to take the derivative of the left-hand side with respect to x, and I'm also going to take the derivative of the right-hand side with respect to x. All right, so if we look at what we have to do first, this 2x cubed is just something that we've been taking the derivative of already, so we'll use our normal methods. That is to say, the 2 is a constant multiple, so the 2 will stay in front, and when we take the derivative of x cubed, we'll have the 3 come in front, so that'll be 6x squared. And this is where we're going to go ahead and consider the chain rule, but we're not going to go through all the steps to replace y with f of x. What we're just going to do is, let's see, we'll have 3. That's the constant multiple, so that'll come down. But what I'm going to do, I'm going to take the derivative of y squared exactly the same way that I would take it if it were x squared. So it would be 2 times y, reduce the power by 1, so it's 2, just 2y. But now I'm going to multiply it by y prime. And again, this y prime came up just because of the chain rule. So instead of f prime of x, we're just using this notation directly instead of showing this chain rule application. All right, so let's go ahead and do the right-hand side as well. So we have the derivative of 8y. So the derivative of 8y would be 8 times the derivative of y. So the derivative of y would be 1, but then we have to multiply that by y prime. So whenever you take the derivative of a variable, other than the variable you're respecting, so in this case we're respecting x, we're going to have to multiply by the derivative, so y prime, or we could have, in the same way, we could have put, instead of y prime, we may have put dy dx or something, and that may have been a little bit more illustrative, but again, let's just go ahead and get the idea down. So let's go ahead and clean this up now, and again, we have to find dy dx, which is the same thing as y prime, so we still have to solve this for y prime. So we have 6x squared minus 6y times y prime. That will be equal to 8y prime. Now, we're going to need to solve for y prime. So what we'll do is we're going to get all of the y primes on the same side. So again, just let's make a note. To get all of the y primes, which is the same thing as dy dx, on the same side. So we'll go ahead and add this 6y y prime to both sides. And on the left, we're left with just 6x squared. On the right, we have 8y prime plus, oh, I forgot the y. So that should be 6y y prime and 6y y prime. And again, note that this y and this y prime are different. Y is just y, something we could plug into, as we'll see in the next slide, and this y prime is what we're asked to find, a dy dx, or the derivative with respect to x. So now that we have the y primes on the same side, we can factor them out. So we have 6x squared on the left, and then we have a 8 plus 6y, and they both have a common y prime next to it. So we could put it there, or we could put it on the front. Either side's fine. We'll go ahead and just leave it over here. And now you can see we're pretty much done. The last thing we need to do is divide everything by 8 plus 6y, 8 plus 6y, and then we have found y prime is equal to 6x squared over 8 plus 6y. Now, this is the derivative. This is dy dx. So we have dy dx, or the derivative of y with respect to x. And, well, let's go ahead and just notice that there's a common 2 in each term. So we could rewrite this as 3x squared divided by 4 plus 3y. And again, that's because every term had a common 2. And for example, if this was a 5 or something, we would not have been able to do this and we would have had our answer, but we have this as the final simplified answer. So that's how you go ahead and use implicit differentiation. Let's go ahead and do a few more examples and just add on to this. But again, remember, we have y prime, dy dx are the same thing. And whenever you take the derivative of a variable other than the one you're expecting, you're going to have to multiply by y prime or t prime or whatever we're going to be using, as we'll see a few more examples. And on the next slide, we're just going to look at a circle. So again, this is the same one as before, except for we've set it equal to 25. We added 25 to both sides. Okay, so let's take the derivative of the left-hand side and the right-hand side. So on the left, we have x squared plus y squared. and that is equal to 25. When we take the derivative of the left-hand side, don't forget we have to also take the derivative of the right-hand side. So the derivative of x squared, the derivative of x squared, and x is the variable we're respecting, is just 2 times x. Okay, plus, now y is still a variable, but it's not the variable we are respecting. So the derivative here is 2y, because again, just pretend this is an x squared. The 2 would come down in front, you reduce the power by 1. But now we have to also remember to multiply that by y prime. Again, that's happening because of the chain rule. And on the right-hand side, the derivative of a constant is just going to be 0. So let's go ahead and solve for y prime now. We have completed step 1. We have differentiated both sides of the equation with respect to x, treating y as a differentiable function of x. So we're going to, now we're going to move on to step 2. We're going to collect the terms with dy dx on one side. And again, remember dy dx is the same thing as y prime. So let's go ahead and realize that we've already collected all of the y primes. So let's just go ahead and solve for it now. So let's subtract 2x from both sides, and we have 2y times y prime, and that will be equal to negative 2x. Lastly, divide both sides by 2y. Oh, let's correct that typo. So we are going to divide both sides by 2y. We find y prime is equal to negative x over y, because the 2's cancel. So there we have it. And we're asked also in this question to find the slope of the circle at this point 3, negative 4. Well, this is a point, so this is an x, this is a y. So if we're going to look for the derivative, we have the derivative, we're going to find the slope, we're just going to plug in 3 and 4, or 3 and negative 4 for x and y. So the actual slope, so you can see this right here, the slope of the tangent line, or the slope of the equation, or of the graph, is minus, and then 3 in the numerator, and then we have a minus 4 in the denominator, and then the 2 negative signs make this 3/4. And of course, we're not asked to find the equation of the tangent line. We could go ahead and do that like we have similarly done in the past. So let's go ahead and just continue to do a few more examples to get the hang of it. I would encourage you to pause the video and try this first, just to see if you get the idea. And again, let me just remind you that we have a product rule that we're going to have to go ahead and work with inside of this sine function. Let's go ahead and take the derivative. Again, we're asked to find dy dx, and again, this is just y prime. We're going to need to use implicit differentiation. This one is going to be a little bit hard to get our hands on because it's squiggly, but we can do it. All right, let's do it. So when we have y squared on the left, and we have x squared plus sine of xy on the right, we're going to differentiate both sides with respect to x. And again, remember that x is our variable we're respecting. So when I take the derivative on the left of y squared, I have 2y, but then I need to multiply it by y prime. The derivative of x squared is just 2x. And this one's a little bit tricky. Notice we have to use the chain rule here. We have an outer function. Our outer function is sine. So remember that the derivative of sine is going to be cosine. So we are going to need to go ahead and remember that chain rule will apply here. And the inside is going to even be a little bit tough because we're going to need to go ahead and take the derivative of x times y. So our inner is x times y. And what is the derivative of x times y? let's go ahead and just work that out up here, just so we don't get lost in the problem. It's a product, so we'll need to do the first. So first times the derivative of the second. So what is the derivative of y? Well, you could just write it as y prime. So, or you could think about it, okay, the derivative of y, thinking about that like it's x is just going to be 1 times y prime, or you may have just directly said y prime. So this is first, this is first, this is the derivative of the second, and then plus the second, which is the y, times the derivative of the first is 1. So this is just going to be xy prime plus y. Okay, let's go ahead and return to the initial problem and remember how to use the chain rule and the product rule and things like that. So the derivative of the outer is cosine, the derivative of sine is cosine, and then remember to bring the inside along. And then we're going to need to multiply by the derivative of the inner. The derivative of the inner, as we computed above, was xy prime plus y. Okay, this is going to be a little bit tough, but let's just keep in mind what we're going to do. We now need to collect all of the y primes on the same side. The problem with this y prime is that it's stuck in this parentheses, and we can't get it out of the parentheses without distributing the cosine through. So this is going to get a little bit messy, but let's just be careful with how we write it. So the left-hand side will be 2y, y prime. The right-hand side, the 2x will come down, but I'm going to distribute the cosine between the two different terms. So we'll have plus xy prime times cosine of xy. Then we'll add to that plus the y cosine of xy. Now, we'll go ahead and solve for the y primes. Let's collect all of those on the same side. So I need to go ahead and I need to take this term over to the other side. There's the cat. So we have 2y, y prime, minus xy prime cosine of x times y. Again, it's negative because I subtracted it to this side. And now on the right-hand side, we still have 2x plus y cosine of x times y. Okay, just like before, we have a common y prime here. So let's factor that out. So when you factor out the y prime, you'll be left with 2y minus x cosine of xy. And that will be equal to 2x plus y cosine of xy. Whew, and we're almost done. The last thing we have to do is divide both sides by this term right here. And we find that y prime, or dy dx, is 2x plus y cosine of x times y, and all of that divided by 2y minus x cosine of xy. This answer really is kind of nice. It has the symmetry of like, here's the 2's, there's the x and the y, there's the y and the x, and then we just have this cosine term. And you may be tempted to like cancel this, but no, you can't. Because again, this is all locked together, so you can't just choose to cancel the xy. Same thing, you can't cancel just the 2's because again, the top and the bottom are all locked together. We could even take multiple derivatives in the same way that we did before. We just have to remember, again, what does it mean to take the derivative of an implicit equation? Whenever you take the derivative of a variable other than the variable you're respecting, so in this case x, we'll need to just go ahead and multiply it by the additional y prime. So again, I would encourage you to pause the video here and see if you can find the first and second derivative. All right, let's go through the computation together. So, of course, to find the second derivative, we need to find the first derivative. So let's go ahead and do that. So we have 2x cubed minus 3y squared equal to 8. And this is very similar to the one we did earlier. It's actually pretty close, except for instead of y here, we just have 8. So let's go through the process again. So let's go ahead and take the derivative of both sides. So when you take the derivative of the left-hand side and the right-hand side, I'm just using prime notation this time, we will find that 2x cubed becomes 6x squared. This becomes minus 6y times y prime, again remembering that we're treating the derivative with respect to x, and the derivative of 8 is simply 0 because it's a constant. So let's find y prime. We will subtract negative 6x from both sides, so we have minus 6y y prime equal to negative 6x squared. Now divide both sides by negative 6, and we find y prime is equal to negative 6x squared over the negative 6y. And of course, quick little simplification, 2 negatives become positive and the 6 cancel. So we have right here the first derivative. Now, to take the second derivative, we'll just go ahead and use the quotient rule. But again, remember, whenever you take the derivative of y, the derivative of y is just going to be 1 times y prime or y prime. So here we go. Y double prime is going to be, well, quotient rule, start low, so it's going to be y squared in the denominator. So it's low derivative of the high, so that's going to be 2x, minus the high, which is going to be x squared, times the derivative of the low, which is just going to be y prime. And we could go ahead and rearrange things, and let's see, here's the one thing we have to watch out for. This is y prime. We know y prime is just this up here, so we'll just do a quick little substitution. So we'll have 2xy minus x squared times y prime, which y prime is x squared over y, and then we have over y squared. So this is y double prime. Typically, it's in bad practice to go ahead and deal with compound fractions because you can see we have this y right here. So to get rid of that, we'll multiply both the top and bottom of the larger fraction by y, and when you distribute, we find that we have 2xy squared because this needs to distribute to both terms. The y cancels in this case of the red, so this is just going to be x to the fourth because the x squared times x squared multiplies x to the fourth. And then we will have just y cubed in the denominator. So a little bit more complicated, but again, similar ideas to what we did before. The derivative of y is y prime. And just remember to do the substitution so that your y double prime is in terms of just x and y, and there's no y primes involved. All right, we have a few more examples. Let's now go ahead and look at this in an application of physics. So look at this, I can see, and the bad joke. All right. So we're going to introduce the idea of a normal line, and a normal line is something we've already dealt with. So let's go ahead and read this statement. A normal line to a curve at a given point is the line that lies, and here's the blank. The blank right here is going to be perpendicular. And is perpendicular to the tangent line to the curve at the point. This line is sometimes also referred to be orthogonal. Orthogonal. So again, we have three words essentially all meaning the same thing. We have a normal line, we have what a normal line is perpendicular to the tangent line. And orthogonal shows up more in multidimensional space. So we're mostly going to be dealing with the word normal or perpendicular. This most occurs in the context of physics, where the way that light enters into a lens. So we have some curved surface here, and let's go ahead and consider the light ray, and we'll find that the point of entry for the light ray is going to be where the normal line and the tangent line meet. And again, they are perpendicular, so they meet at a right angle. Then, of course, instead of it going straight down, when it hits the lens, that normal line will extend through into the lens, and you'll have two angles, alpha and beta, or A and B here. And you could then go ahead and find those using some trigonometry. So let's go ahead and look at how to go ahead and find the tangent and the normal line. This should be pretty familiar because, well, we already know how to find the tangent line. And to find the normal line, we're just going to have to adjust the slope. So let's do that. Of course, I would encourage you to pause the video here and just see if you're able to go ahead and figure it out. So I'm going to also have two slides here because it looks like it's going to be a little bit, there's quite a bit to write here, so let's go ahead and make space for that. So we need to go ahead and find the tangent line. So in order to do that, we're going to need to take the derivative. So that's one thing we're going to have to do. This is actually the second thing we asked to do. We're also have to find the normal line. The first thing we're asked to do is to show that this point lies on this curve. And again, what does it mean for, what does this mean? If it's going to be on the curve, when you plug the 2 and the 4 in, which is an x and a y value, into this equation, you need to make sure that it's true. So for the first part, again, what we're going to do is we're going to plug the point 2, 4 into the equation to determine if it's on the curve. Determine if it's on the curve. And, well, if we look ahead, we can see that it is on the curve. In that bottom right-hand corner, we'll see the picture, and 2, 4 is on this curve. But let's go ahead and verify it algebraically. That is to say, we're just going to do, plug in 2 in for x, so 2 cubed plus 4 cubed, so this was x, this is y, minus 9 times 2 times 4. Is that equal to 0? Well, 8 plus 64, and then 9 times 2 is 18, and 18 times 4 is 72. So minus 72, is that equal to 0? Well, yeah, it's true. Because that is true, we do know that 2, 4 is on the curve. All right, part 2 has quite a bit to do. We have to go ahead and find tangent. And then, of course, once we find the tangent, we'll go ahead and need to go ahead and plug it into like point slope form to actually get the line. All right, so here we go. Take the derivative of this equation, x cubed plus y cubed minus 9xy equal to 0. Take the derivative of both sides, and we're going to be treating it with respect to x, whatever is our horizontal axis. So we have 3x squared plus 3y squared times y prime. Then here we have to use the product rule. So we have minus 9, and I'm going to do the product rule for this x times y, same as before. First times the derivative of the second, plus the second times the derivative of the first. So that gives us the derivative of x times y, and that will be equal to 0. So at this point, we just need to go ahead and distribute the negative 9, move things around, and solve for the y prime. So we have 3x squared plus 3y squared, y prime. Oops, forgot the y prime right there. So let's fix that. Then minus 9xy prime minus 9y equal to 0. Now, let's go ahead and get the terms with y prime on one side and those without y prime on the other. So we'll go ahead and subtract the minus 3x squared from both sides and add 9y to both sides. In doing so, we have 3y, here I'll keep that in color blue. We have 3y squared minus 9x, and again, those both have a common y, so our y primes will factor out the y prime, and that will be equal to what we just subtracted and added to the other side, the minus 3x squared plus 9y, and then lastly we find y prime is equal to minus 3x squared plus 9y, and all of that over 3y squared minus 9x. So it took us a little while to get there, but indeed we got there. So we could go ahead and factor out a common 3 if we want, but of course what we need to go ahead and do is figure out what is the slope. So to figure out what is the slope, we're just going to take the point and plug it into the derivative. So we could rewrite this as like f prime of 2, 4. And when we plug this in, we would have minus 3 times 2 squared plus 9 times 4. And then all of that divided by 3 times 4 squared minus 9 times 2. When we simplify this, this gives us 4/5. And this is the slope for the tangent. And of course, if for the normal, we just have negative 5/4, the negative reciprocal is the slope for the normal line. So of course, this doesn't quite give us the actual line that we're asked for. This just gives us the slope of them. And again, the 4/5 is the slope for the tangent line because we plugged 2, 4 into our derivative. And the normal line, by definition, is perpendicular to the tangent. Since it's perpendicular, you take the negative reciprocal. So the last thing we need to do, and we will go ahead and just fit it on this page right over here. So the actual process of finding the point slope form or finding the equation. So you would just do y minus 4 equal to 4/5. And this would be x minus 2 point slope form. Solving this, we find y is equal to 4/5x and then plus 12/5. So this is, of course, your norm, or this is your tangent line. And then your normal line, well, is going to be y minus 4 equal to negative 5/4 times x minus 2. And when we solve that for y, we find y is equal to negative 5/4x, and then plus, after everything is simplified, 13/2. So that is your normal line.